What really happened when the largest tsunamis in history hit the Earth? Dear traveler, greetings. Dear traveler, greetings. Today, we lift the veil on colossal waves, far beyond anything humanity has ever known. Titanic walls of water, taller than modern skyscrapers, rushing at hurricane speed, engulfing continents and erasing in an instant everything in their path. But before we embark on a new adventure, don't forget to like the video and subscribe to the channel to not miss anything. Thank you, and have a nice trip. About 4.5 billion years ago, our planet was just a massive cluster of molten matter, shaken by violent impacts and heated from within. Imagine a lifeless world, bathed in the red glow of a forming Earth, far from the blue planet we know today. At that time, the Earth's crust did not yet exist, and heavy volcanic gas clouds covered the surface. Temperatures often exceeded hundreds, if not thousands, of degrees Celsius. In the beginning, the Earth's interior contained many radioactive elements with short half-lives, whose decay produced intense heat. Combined with the energy from collisions with other celestial bodies, this heat maintained a vast ocean of magma, a reservoir of molten rock. Unlike our water oceans, this magma ocean was a fluid mass of melted minerals. Under the enormous pressure exerted by the planet, heavy metals migrated towards the center to form the core. At the same time, lighter elements, like silicates, formed a still partially liquid mantle. Even unstable, this ocean of magma was subject to gravity, which strove to organize the internal layers. Powerful convection movements where hot matter rose before cooling and descending again. They literally boiled the surface. These circulations sometimes created thin, rigid plates, often quickly disintegrated by the heat. But some more solid fragments resisted, like rafts floating on the molten rock. These first islands of solidity, sometimes able to retain a little water, are today called proto-oceanic basins. Primitive Earth already contained water, although its exact origin remains debated. Some researchers attribute it to chondrites, meteorites rich in volatile elements, or to comets that bombarded the planet. Under the effect of the heat, this water first existed in vapor form. Then, as it cooled, it formed thick clouds, giving rise to torrential rains. When the surface became solid enough, the water accumulated in puddles or temporary ponds. These were the first traces of the oceans to come. Before the situation stabilized, the young Earth experienced a heavy, late bombardment between 4.1 and 3.8 billion years ago. During this period, a rain of asteroids and comets struck the planet at vertiginous speeds, releasing enormous energy. These impacts carved out immense craters and hurled molten rock into the atmosphere. Shockwaves lifted giant magma waves, similar to tsunamis but without water, true magma tsunamis, born from the extreme violence of these collisions. In the rare areas where water began to form, the shocks caused by the impacts could raise gigantic waves, sometimes estimated to be more than 10 kilometers high in extreme cases. Although no human witness observed these events, fluid dynamic simulations that model the behavior of liquids according to pressure, temperature, and gravity suggest that a major impact could create true mountains of water. The early seas were constantly churned, hurled, and shaken, well beyond what modern tsunamis produce. During the late bombardment, the Moon, then closer to the Earth, was also struck by violent impacts. The most famous, the South Pole Aitken Basin, is on its far side. Some researchers think a similar terrestrial crater could have existed at the same time, although traces have likely been erased by tectonics. To trace it, scientists use geophysics and modeling. They are particularly looking for breccias, rocks formed of welded fragments. In this context, we speak of Archean tsunamite breccias, possible vestiges of giant waves dating from this distant era. These breaches are fascinating because they may reveal the imprint of gigantic waves at a time when Earth was undergoing significant transformation. Scientists draw parallels with current deposits left by tsunamis. These deposits are disorderly layers of sand, gravel, and rocks. In the Archean rocks, these atypical structures are sometimes found, indicating a sudden rather than slow deposition. By analyzing the chemical composition, fragment size, and shock-related deformations, researchers are gradually piecing together the grand puzzle of our geological past. Despite the violence of the early mega-tsunamis, the Earth was slowly cooling down. The heat accumulated in the mantle was escaping to the surface and then into space. As impacts became less frequent, the crust had more time to solidify. As temperatures gradually decreased, liquid water could remain longer. The hydrosphere, meaning all the water present on the surface in the form of vapor, clouds, liquid, or ice, began to stabilize. Gradually, water was taking precedence over magma, heralding a new face for the planet. From then on, tsunamis were no longer just waves of magma, but true waves capable of raising the liquid water of future oceans. These were the first hydrospheric tsunamis, which, despite their difference, could reach gigantic sizes, reflecting a still tumultuous world. Earth was finally structuring itself with a distinct metallic core, a solid mantle, fragments of continental crust, and a surface rich in water. Life, still tiny and microscopic, was beginning to pave the way towards an emerging biosphere. Imagine an observer on a small islet of solidified crust, surrounded by thick vapors where magma still boils in places. The air, loaded with carbon dioxide, would make breathing impossible for a modern human. Salty water droplets fall, flowing towards small boiling lakes. Suddenly, an asteroid strikes the horizon, causing a violent tremor. The rock shakes, cracks, and immense waves form. From space, one would see vast dust plumes rising, while the sea lifts a hill of water several kilometers high, carrying away rocks and mud. This wild chaos lasts a few hours before water vapor covers the scene. After each impact, Earth continued to slowly dissipate its heat. Its faster rotation than today created a day-night alternation, fostering surface cooling. Gradually, these unstable cycles gave way to longer periods of stability. It was then, at this turning point between volcanic hell and a milder climate, that microbial life could have emerged. Nestled between forming ridges and hardened crust, zones offered a chemical and thermal refuge conducive to the formation of complex molecules. For the majority of scientists, life probably began in water, protected from bombardments and radiations by a still thin atmosphere. The very first mega-tsunamis, whether magmatic or hydrospheric, play a key role in Earth's history. They reveal the colossal energy of the collisions that shaped our planet and illustrate the extreme fluid dynamics of that time. These events sculpted the nascent surface while mixing and redistributing essential elements like iron, silicon, sulfur, and magnesium. This redistribution subsequently influenced mineral evolution and perhaps even the appearance of the first prebiotic structures. When we think of tsunamis, we often envision powerful water rolls on a coast, But at that time, the edges of proto-oceanic basins were far from stable. They were cracked, covered with partially solidified lava, and littered with cosmic dust fallen after each impact. The waves, although confined to these often deep but narrow basins, could grow rapidly. The moon already influenced the nascent tides, adding a complexity that amplified these water movements, even if they remained irregular and less powerful than today. Studying this past requires a combination of geochemistry, petrology, the study of rocks, and numerical modeling. For example, hydrodynamic modeling attempts to simulate the reaction of a fluid to an impact, taking into account gravity, density, topography, and released energy. However, reconstructing the topography of early Earth is a major challenge, as the evidence has vanished under tectonics. Researchers are thus exploring several scenarios to gauge the probable extent of these events. This panorama reveals a clear sequence. As Earth adjusted to collisions, they became less frequent, allowing liquid water oceans to expand. When the planet was too hot, water was mostly in vapor form or trapped in magma. With the appearance of areas cold enough, water could accumulate in vast expanses. This transition, key in Earth's history, marks the end of magmatic tsunamis, replaced by hydrospheric tsunamis, as the sea of rock became scarce and liquid water became the target of cosmic impacts. These hydrospheric tsunamis lay the groundwork for many phenomena to come. For now, let's simply acknowledge the birth of a water cycle, still embryonic, yet already capable of generating marine tsunamis. Each major impact, eruption, or tectonic collapse could then lift, move, or even heat these bodies of water, causing colossal disturbances. By the end of this period, between 3.8 and 3.5 billion years ago, Earth, though still restless, tends towards a lull. Solid surfaces extend, allowing rain to flow over more stable terrains. The seas grow, promoting the formation of true oceanic zones. Models show that the extreme temperatures of several thousand degrees dropped to a few hundred on the surface, then decreased further with the progressive cooling of the planet. In these primitive seas, microscopic organisms could develop. These are simple bacteria capable of drawing energy from minerals, or perhaps thanks to nascent photosynthesis. Although it is difficult to specify their nature and abundance, it is plausible that they survived in areas protected from mega-tsunamis, such as coves flanked by volcanic reliefs acting as natural dikes. At this stage, no visible plants, animals, or algae yet existed. The world was microscopic, dominated by nascent chemical reactions. The sequence ends with a calming Earth, where our world begins to take shape. The gigantic magmatic tsunamis fade away, replaced by immense waves of liquid water. Beneath the surface, mantle movements continue, preparing the drift of continents, the opening of oceans, and the formation of future mountains. It is during this transition that future seas take shape, and the water cycle becomes essential in shaping the geology of the planet. In conclusion, the earliest mega-tsunamis played a crucial role in the dispersion of minerals and the transformation of Earth's surface. They recycled matter, carved and filled basins, and initiated sedimentation in areas where water altered molten rock. The slow stabilization of the hydrosphere finally allowed Earth to leave this initial chaos to enter a world where water, now settled, offered a possible cradle for life. In this titanic story, the forces at play exceed any human imagination. They remind us how much our planet has gone through extreme trials before offering a gentler refuge. Today, as we walk on stable ground, we are the heirs of a past where fire and water clashed, shaping the framework of a habitable gem, the cradle of a thriving biodiversity. Thanks to research and interdisciplinary exploration, we understand how this primordial violence gave way to life. Between 3.5 and 2.8 billion years, Earth experiences significant upheavals, leading to the formation of the first stable oceanic crusts. We are then in the Archean Eon, between the Eoarchean and the Mesoarchean. The surviving rocks of this era are rare, but they testify to a planet marked by intense internal heat and differentiation processes. During this period, continents gradually form, and microbial life develops in various marine environments. Earthquakes, local subductions, and tsunamis begin to shape the shores. To better understand, let's explore the nascent tectonics, primitive volcanism, and traces of powerful ancient waves. Tectonics refers to the movements and deformations of the Earth's crust. At the beginning of the Archean, internal heat, due to the decay of radioactive elements, fuels intense geological activity. Primitive rigid plates appear, capable of overlapping or fitting together. Subduction, where a denser plate sinks beneath another, remains difficult to prove at this time. However, the presence of high-pressure metamorphic rocks suggests these zones. These early subductions promote the circulation of materials between the surface and the mantle, laying the foundations for future continents. Intraplate earthquakes, which strike the very heart of the plates, probably existed as early as the Eoarchean. They result from the reactivation of ancient fractures or local thermal stresses. When a powerful earthquake shakes the ocean floor, it can generate a fast-moving wave. According to modeling, these primitive tsunamis would reach between 30 and 100 meters, depending on the depth and configuration of the margins, although this figure remains hypothetical. Primitive arc volcanism is also a driver of tsunamis. During subduction, the sinking plate releases water and gas into the mantle, lowering the melting point and creating magma. This magma feeds volcanoes forming island or continental arcs. Vast basaltic plateaus result from the outpouring of fluid lava. When these accumulations become unstable, massive landslides can cause sectorial tsunamis, submerging nearby shores and heavily reshaping sediments. To identify these paleo-tsunamis, geologists study sedimentary deposits from the Eoarchean and Mesoarchean. Banded iron formations, composed of alternating layers rich in iron oxide and silica, are common. When they show reverse grading, it indicates a sudden event that disrupted normal sedimentation. These inverted rhythmites suggest the passage of a powerful wave, likely tsunami-generated. Acuminated quartz flakes are another valuable clue. These fragments show breaks indicating strong mechanical stress, probably related to the impact and rapid abrasion of a tsunami. Geologists compare them to similar structures in more recent tsunami origin deposits. However, it is sometimes difficult to distinguish the effects of a giant wave from those of an extreme storm, as both leave coarse sands, disrupted layers, and erosion marks. The key is to analyze several textural and contextual criteria together. Detecting these very ancient traces poses a real challenge. The rocks have often been altered by metamorphism, tectonic folding, or magmatic intrusions, partially erasing the primitive clues. Tsunami deposits may be laminated, recrystallized, or destroyed. Additionally, violent storms produce similar deposits. Therefore, reliance is placed on geochemical signals, such as angular minerals or isotopic signatures, to reinforce the hypothesis of a rapid wave. To strengthen their conclusions, specialists examine the microstructure of sediments, their chemical composition, and the organization of layers. They also analyze the geological context, which includes the presence of volcanic arcs, subduction zones, or faults. Identifying a particular deposit in an unstable margin suggests that a landslide or earthquake generated the wave. They also search for volcanic inputs or associated hydrothermal compounds. At this time, life is probably limited to microscopic forms, such as prokaryotes and a few primitive eukaryotes. Tsunamis could have disrupted their habitats by redistributing sediments and altering the chemistry of shallow waters. Microbial colonies, of which stromatolites are the most visible fossils, developed through photosynthesis. These powerful waves could fragment these bacterial mats and change the distribution of nutrients. Their role in the dispersion of early organisms remains speculative, however, due to insufficient records. Emerging earthquakes and embryonic subduction are not just hypotheses. They impact the organization of volcanic platforms. Primitive arcs already show the current dynamics: partial mantle melting, volcanic island emergence, crust creation, then collapses. Basaltic plateaus formed by superimposed flows can become unstable. A steep edge, an imbalance, or an earthquake can trigger a massive collapse, causing a sectorial tsunami. One might think that the limited size of Archean oceans would prevent dangerous waves. However, the movement of pebbles and intermingled layers suggests tsunamis. Paradoxically, restricted basins or those populated with volcanic islands can locally amplify wave height. The coasts, still poorly defined, then undergo strong morphological reconfigurations. During the Eoarchean and Mesoarchean, the Earth continued to cool slowly, but its mantle remained much hotter than today. Volcanic gases enriched the atmosphere, making the climate probably warmer despite a less intense sun. Surface waters exceeded 30 degrees, favoring some chemical reactions and microbial growth in specific niches. This context also saw the emergence of more stable tectonic plates, initiating a lasting cycle. Faced with the complexity of these mechanisms, researchers combine field geology, laboratory analyses, and numerical simulations. Radiometric dating on zircons helps date Archean rocks. Comparisons with recent environments offer a framework to interpret the structures. Typical sequences are sometimes observed: clear erosion surfaces, deposits of coarse sands, then a return to fine sedimentation. These disturbed microlaminations and levels of basaltic debris reveal ancient tsunamis. These studies uncover a constantly moving planet. Far from being a modern phenomenon, tsunamis have shaped Earth's dynamics since ancient times. They mold coastal geomorphology and influence the nascent biosphere. Even microscopic life was marked by these colossal waves. Between 1 billion and 541 million years ago, Earth went through an intense geological and climatic phase. The supercontinent Rodinia grouped almost all the land masses, forming a vast rocky plateau with mountainous chains in formation. Marine ecosystems were underdeveloped, life being limited to microscopic organisms and a few simple multicellular forms. The atmosphere contained less oxygen and more carbon dioxide, with temperatures varying greatly by region. Under tectonic forces, Rodinia fractured, opening new oceanic basins. These movements triggered global mega-tsunamis that violently struck the nascent coasts. As Rodinia fractured, immense pressures were exerted in depth, triggering powerful earthquakes on the unstable edges of continental fragments. Under these tremors, newly forming ocean basins saw massive water movements, creating long and swift tsunamis. Models suggest these waves could reach several tens or even hundreds of meters when approaching the coasts. Although geological evidence is fragmentary, it is plausible to imagine these devastating waves submerging coastal environments, carrying sediments and rock blocks. While these events caused major ecological disruptions, marine life was still too limited for their impacts on biodiversity to be considerable. During the Neoproterozoic, Earth experienced extreme glaciations known as Snowball Earth. According to this hypothesis, the planet was almost entirely covered in ice, even reaching the equator. The Sturtian glaciation, around 715 million years ago, and the Marinoan glaciation, around 635 million years ago, are among the most intense global cooling episodes in Earth's history. Vast ice shields covered land and oceans, extending the ice cap well beyond the current poles. Temperatures sometimes plummeted to several tens of degrees below zero, transforming the surface into a desolate white desert. Yet beneath the ice, life persisted in marine refuges, notably near hydrothermal vents. Each deglaciation provoked major upheavals, durably shaping the planet's evolution. During these intense glaciations, immense quantities of ice accumulated on the continents and oceanic plateaus, forming thick ice caps. Sometimes, local warming or a weakening of the structure caused the sudden collapse of part of these frozen masses. Imagine then a gigantic wall of ice, breaking in a few seconds, suddenly releasing a colossal flow of water, and icy fragments rushing at full speed. This phenomenon, comparable to the Icelandic Chicxulub, could generate true tsunamis under the ice cap. These titanic waves propagated under the floating ice, raising the waters to distant shores where the ice gave way to rocky coasts. Although their direct trace is difficult to detect in geological records, certain sedimentary deposits testify to the combined action of ice block falls, melt currents, and raging waves. These phenomena undoubtedly contributed to shaping the coastal and marine landscape of the Neoproterozoic. Scientists reconstruct these ancient events by studying rocks. Clues like dropstones, disturbed varves, and chaotic conglomerates testify to an agitated glacial past. Dropstones, rocky blocks deposited in fine sediments, come from floating ice, witnessing the drift of icebergs far from their origin. The varves, annual sedimentary layers, show interruptions caused by sudden events such as tsunamis or violent currents. Chaotic conglomerates, a disordered mix of blocks and pebbles in a fine matrix, indicate rapid deposits related to underwater landslides or debris flows, often associated with glacial dynamics and mega-tsunamis. Beyond geological traces, the glaciations and tsunamis of the Neoproterozoic profoundly influenced the ocean's chemistry. During the Snowball Earth periods, ice covered much of the globe, limiting atmosphere-ocean exchanges and reducing the light penetrating the water. Photosynthesis slowed down, and the waters under the ice often became oxygen-poor. When the ice melted, sometimes abruptly, immense volumes of nutrient-rich water were released, causing nutrient pulses that stimulated massive plankton growth. This biological explosion increased oxygen production at the surface, gradually modifying oceanic chemistry, and favoring the emergence of more complex life forms. The combined action of tsunamis, glacial melting, and chemical upheavals also influenced the dynamics of continents. The retreat of ice caps lightened the Earth's crust, causing an isostatic rebound, meaning the surface gradually rose. In a tectonic context already fractured by the breakup of Rodinia, this uplift could trigger underwater earthquakes and consequently new tsunamis. A cycle then set in: local warming, partial melting, glacial collapse, release of water and sediments, tsunamis, and shoreline modification. This reorganization gradually shaped the conditions of marine sedimentation and favored the emergence of habitats conducive to life. With a climate that gradually became milder, new ecological niches could emerge, heralding an upcoming biological diversification. During the Neoproterozoic, although complex organisms were rare, environmental upheavals strongly influenced life evolution. The chemical variations of the oceans, associated with glaciation and deglaciation cycles, created habitats favorable to the emergence of new life forms. During interglacial periods, the opening of waters to light and the abundance of nutrients stimulated the proliferation of microorganisms in previously barren areas. Gradually, simple unicellular and multicellular organisms experimented with new ways of life. Even though fossils are rare, some clues suggest a diversification of forms fixed on the seabed, notably algae and bacterial colonies. Thus, the alternation between Snowball Earth and warmer phases acted as a catalyst, preparing the emergence of more complex organisms in the Ediacaran and beyond. We find ourselves projected between 541 and 444 million years before our era, from the Cambrian to the Ordovician. It was a fascinating time when the first continents and ocean basins were taking shape, far from their current configuration. Two major oceans dominated the scene, Iapetus and Panthalassa. The atmosphere evolved, while marine life began to diversify, especially on the sea floor. Tectonics was intense. Plates moved, pulled apart or collided, shaping mountain chains and marine spaces. In this context, passive margins formed and disappeared, where the plates drifted apart without subduction, and active margins, triggering seismicity and volcanism. These developments favored the opening of new oceans and the building of vast carbonate structures on the continental shelves. To visualize this well, the Iapetus Ocean separated two budding landmasses, corresponding to future Proto-European, Proto-North American, or Proto-Gondwanan blocks. At that time, a high sea level flooded vast regions. The crusts, thinner and often warmer, favored their fracturing. The Iapetus Ocean thus expanded through oceanic opening. Lava rose at the ridges, creating new crust. Meanwhile, the Panthalassa Ocean covered a vast portion of the globe, prefiguring today's Pacific Ocean. The ridges, sites of intense eruptions and earthquakes, could trigger tsunamis, propagating at several hundred kilometers per hour to strike the coasts with immense energy. In this primitive setting, massive landslides could occur on the vast carbonate platforms, like the famous Great American Carbonate Bank. This huge, shallow marine zone slowly accumulated calcium carbonate-rich sediments derived from marine creatures with calcareous shells or skeletons, such as certain sponges, brachiopods, and microscopic algae. Over time, these deposits formed thick platforms extending over hundreds or even thousands of kilometers. However, these massive structures remained fragile. Tectonic or seismic activity could crack their base, causing the sudden collapse of vast volumes of rock and sediment. This violent landslide would then generate a tsunami, propagating in all directions over long distances. During the Cambrian and Ordovician, tsunamis mainly affected coasts close to the carbonate platforms. These coastal areas housed a diverse benthic fauna, fixed organisms like primitive corals and sponges, as well as mobile creatures such as certain arthropods and mollusks. Among them, trilobites were emblematic, with their segmented bodies and three-lobed carapaces. These animals fed on organic particles on the seafloor and colonized various environments, from shallow waters to deeper zones. During a tsunami, lacking means of escape, they risked being buried under displaced mud or thrown elsewhere. These colossal waves often caused local mass mortality, making the environment hostile by mixing sediments, altering salinity, and with the violence of currents, leaving only the most resilient species to survive. To identify these events in geological records, paleontologists and geologists rely on several indicators. The Burgess Shale series in the Canadian Rockies is famous for its exceptional preservation of soft-bodied fossils, revealing the detailed morphology of rarely preserved animals. Beyond its biological richness, this formation presents intriguing sedimentary signatures. Among them, disrupted inverse laminations indicate rapid and powerful action. Inverse laminations designate sedimentary layers where fine particles are above coarser ones, like those of a reverse current. The chevron folds, nearly symmetrical V-shaped folds, also testify to rapid and repeated constraints, often linked to high-energy waves. When researchers identify these inverted laminations and chevron folds in the strata, they seek to determine whether they are signs of classic violent storms or true tsunamis. Storms also generate powerful waves, but their sedimentary signatures often differ. A tsunami generally starts by eroding the surface, removing large quantities of sediments, and redistributing them near the site of collapse. Several waves then follow, each capable of reshaping particle distribution. The chevron folds reflect these repeated energy pulses. Researchers sometimes compare these stacked layers to the pages of a book suddenly overturned, each page folding under a wave of different intensity. The precise analysis of the thickness, position, and composition of the sedimentary layers helps differentiate a classic storm from a tsunami surge. Paleo-earthquakes, ancient earthquakes that occurred millions of years ago, often leave these traces, especially when their epicenter is in a marine environment. During the Cambrian and Ordovician, seismic events related to oceanic expansion multiplied. The tectonic plates of the Iapetus and Panthalassa oceans constantly moved, creating new rocks and generating faults. The tsunamis from these earthquakes propagate at an average speed of 600 to 800 km/h, surging like a wall of water, capable of crossing in a few hours the distance between a continental platform and a distant shore. In the event of a massive landslide on the edge of a carbonate platform, the wave amplifies and devastates coastal areas. These tsunamis could have caused significant local extinctions, wiping out several benthic species such as trilobites, sponges, or brachiopods. Although these events leave few direct traces, the simultaneous disappearance of these organisms in certain geological layers suggests a brutal catastrophe, likely a tsunami. These local extinctions, called first-induced extinctions, do not affect the whole planet, but profoundly disrupt regional ecosystems. The Cambrian and Ordovician benthic fauna see their food chain disrupted, with bottom-dwelling organisms, the prey of predators, being decimated. These vacant spaces are then colonized by opportunistic species that can diversify and thrive, making tsunamis paradoxical drivers of local evolution. Fossil records testify to this ecological reorganization with disappearances and appearances of species. Trilobites, in particular, illustrate this dynamic, with some groups becoming locally extinct, while others adapt and colonize new environments. Throughout the transition from the Cambrian to the Ordovician, marine environments became more complex with the appearance of more elaborate planktonic algae, primitive corals, and an increasing number of mollusks. This diversification intensifies, but earthquakes and tsunamis persist as tectonics continue to renew the oceanic crust and transform continental margins. Marine life remains exposed to these geological catastrophes, which periodically displace numerous species. Tsunamis, submarine landslides, volcanic eruptions, and other calamities contribute to shaping and reshaping marine populations. Some areas become refuges, while others regularly experience severe disturbances. Distinguishing a storm deposit from a tsunami deposit remains difficult, as storm and tsunami waves both produce strata that mix sand, mud, and debris, as well as unusual laminations. Geologists search for subtle clues: the extent of the disturbance, the thickness of the reworked layers, the direction of the force, or the presence of fossils displaced over long distances. Chevron folds indicate rapid oscillations, typical of a tsunami bouncing off the shore. The repetition of several similar episodes, close together in a sedimentary sequence, suggests successive waves linked to the same major seismic event. Inverted laminations indicate a current capable of remobilizing already deposited sediments, characteristic of giant tsunamis. Thus, the detailed analysis of sedimentary sequences often reveals a complex narrative of sudden events, sometimes followed by phases of ecological reconstruction. Tsunamis during the Cambrian and Ordovician caused significant ecological disruptions. The landslides on carbonate platforms destroyed sedentary fauna and disrupted filtering organisms. Trilobites, living on shallow seafloors, were often buried or displaced, but some more mobile groups survived. This led to an ecological reorganization, where new families colonized the vacant niches. This phenomenon, observed in different terrains, was reinforced by the movement or assembly of these continental blocks, favoring the evolution of some species and the extinction of others. The first local extinctions induced by tsunamis illustrate the major impact of geological upheavals on marine evolution. At this time, life was beginning to become more complex, and each catastrophe offered an opportunity for organisms capable of colonizing the disturbed environments. The Burgess Shale series hold the memory of these dramas, witnesses to the powerful forces that shook the ocean floors. The Cambrian and Ordovician appear as a vast canvas of evolutionary experiments. Tectonic, biological, and climatic events gradually shaped the planet, while the marine biosphere was built, dismantled, and rebuilt with the confrontations between land and sea. This fascinating chapter reveals the close interaction between geology and marine life. The earthquakes related to the expansion of the Iapetus and Panthalassa oceans not only disturbed sediments, but also profoundly affected benthic fauna. Nature shows remarkable resilience. After the wave and turbidity, life resumes, colonizes the cleared spaces, and thrives. These catastrophic episodes thus led in the long term to a beneficial overhaul of biodiversity. Across the strata and fossils, these tens of millions of years appear as a key period where tectonics, oceanography, and biological evolution combine to shape a world very different from ours. The identification of inverted laminations and chevron folds in the Burgess Shale and other contemporary formations goes beyond simple geological classification. These structures testify to a constantly moving Earth, generating instabilities, leading to major tsunamis. The local extinctions superimposed on them are understandable in view of the vulnerability of primitive marine communities, dependent on precise environmental conditions. A tsunami can not only eliminate organisms but also bury reproduction areas under several centimeters of mud. The ensuing ecological reset paves the way for new evolutionary lineages, ready to colonize these devastated environments. At the junction of the Cambrian and Ordovician, the Earth experienced a constant cycle of margin building, localized carbonate platform collapses, and earthquakes capable of shaking entire oceans. The first great benthic faunas are both victims and actors in this geodynamic dance. Victims because they suffer these disruptions. Actors because their local extinctions or resurgence contribute to the recomposition of life, enriching marine biodiversity. Today, scientists are continuously studying new Cambrian and Ordovician fossil sites to better understand the role of tsunamis and earthquakes in evolution. Through advanced analyses, such as sedimentary coring and computer simulations, they refine understanding of the enormity of the events, the speed of the waves, the height of the waves, and the trajectory of currents. These Cambrian-Ordovician tsunamis remain a crucial key to understanding how nature has always, sometimes brutally, intertwined geological movement and biological evolution. The Silurian, from 444 to about 410 million years ago, is a key period in Earth's history. During this time, coastal areas gradually stabilized, while marine life continued to expand. Coastal environments evolved under the influence of tectonic dynamics and the emergence of new forms of life, thus preparing for the major transformations that would culminate in the Devonian. The Devonian, from 416 to 359 million years ago, is nicknamed the Age of Fish. The oceans experienced an explosion of biodiversity with the diversification of ray-finned and lobe-finned fishes. On emerging lands, the formation of more complex soils and the appearance of the first trees gradually transformed the landscapes. The coasts then became dynamic exchange zones between sea and land, promoting the emergence of unique and well-established coastal ecosystems. One of the major advances of the Devonian was the appearance of the first forests. While vascular plants like Cooksonia already existed in the Silurian, they remained small and confined to humid environments. At the beginning of the Devonian, larger and more structured vegetation emerged, with Archaeopteris as its emblem. This primitive tree developed a thick trunk, an extensive root system, and leafy branches, heralding the forests to come. The presence of the first forests on the coasts of Paleo-America created a new protective environment against violent marine phenomena. During a tsunami, caused by an earthquake or a coastal collapse, the barrier formed by trees and shrubs slowed down the force of the waves. The solid trunks, deep roots, and dense foliage increased friction, slowing the water flow and limiting damage to coastal plains. In the Silurian and Devonian, tsunamis often resulted from tectonic instabilities, volcanic eruptions, or asteroid impacts. The coasts then suffered violent floods, whose traces are sometimes visible in sedimentary deposits. Deltas and estuaries, particularly vulnerable, benefited from the crucial role of pioneer vegetation that held sediments in place and limited erosion between two major tsunamigenic events. During the Devonian, two asteroid impacts marked the geological history of the Earth. The first, which occurred about 377 million years ago, is linked to the Silurian crater in Sweden. The second, dated to 364 million years ago, corresponds to the probable Woodley crater located in Western Australia. Although separated in time and space, these impacts profoundly disrupted coastal areas, triggering immense tsunamis, some exceeding 200 meters in height due to the massive displacement of waters. Modern simulations based on virtual basin models show that such impacts would have projected immense columns of water. These waves would have traveled hundreds of kilometers inland, especially on the coasts of the supercontinent Gondwana. Where vegetation was absent, the shores suffered the direct assaults of tsunamis. In contrast, wooded areas offered some protection. Although fragmentary, sedimentary traces reveal the magnitude of these marine catastrophes and their effects on coastal life. At that time, the coasts of Gondwana featured great diversity: sandy beaches, floodplains, emerging reefs. During an impact tsunami, the sea would cross these shores over long distances, resulting in a mix of marine and terrestrial sediments. Macro debris such as pebbles, broken shells, and even huge blocks torn from cliffs can be found. These brutal incursions caused major ecological upheavals, exterminating the less mobile species of shallow waters and making way for new balances during recolonization. Among the evidence sought by geologists and paleontologists are tsunami-ites, characteristic deposits formed by the brutal action of a tsunami. In the Murrendal group in Australia, striking examples are observed in the form of coarse sandstones containing intraclasts, fragments of sediments ripped from already hardened layers. These materials are suddenly deposited in sandy layers, sometimes accompanied by lode structures like traces of sinking, indicating a rapid deposit under intense hydraulic pressure. The lode structures in these deposits take the form of bubbles or inverted waves, resulting from the sudden pressure exerted by heavier layers on softer sediments. During a tsunami, the massive arrival of water loaded with particles accentuates this phenomenon. These intraclast-rich sandstones are noticeably different from those left by coastal storms. They extend over larger areas and bear the marks of currents, with power well beyond that of typical marine storms. These observations offer valuable insights into the power of ancient tsunamis and their ability to rapidly transform landscapes. In the Murrendal group, thick sandstone layers alternate with finer sediments, revealing a pattern of violent phases followed by calm periods conducive to tranquil deposits. Today, researchers analyze these sequences to validate their models by studying the thickness of layers, stratum inclination, and the distribution of intraclasts to trace the dynamics of each destructive wave. The tsunamis of the Silurian and Devonian eras did not only affect the marine fauna attached to reefs. Fish, particularly Sarcopterygians, ancestors of tetrapods, also suffered from their impact. Their thick fins, supported by bony structures, provided them with a certain robustness against turbulent waters and perhaps even the ability to move across unstable grounds. Despite these advantages, the extreme violence of the tsunamis could lead to mass mortalities, affecting even those species better equipped to resist. When the wave hits, it sweeps away sediments, marine creatures, and debris of all kinds. Many fish are caught in the whirlpools, unable to fight the powerful currents. However, once the violence subsides, survivors can discover new habitats exposed by erosion. The retreat of the waters sometimes creates temporary pools, expanded coves, or redesigned channels. These microenvironments, born of chaos, then become ideal refuges for the rapid recolonization of species. Thanks to their sturdy fins and their ability to partially breathe air, some sarcopterygians, like lungfish or dipnoans, were well equipped to handle post-tsunami upheavals. In the Devonian, this dual respiration offered them a significant advantage in shallow and unstable areas. They could quickly recolonize the transformed environments, slipping between silt deposits or settling in calmer lagoons, temporarily cleared of predators. The dispersion of sarcopterygians is also explained by the unstable geography of the time. The ongoing continental drift regularly opened new marine basins and reshaped coastlines, sometimes even by the rotation of crustal blocks. A tsunami, beyond local destruction, could thus propel resistant species to other shores. Some fish, projected into lagoons or flooded valleys, would then find favorable zones to establish and develop, provided the environment remained suitable. In forested areas, tsunamis did not only have destructive effects. They sometimes facilitated the dispersal of seeds well beyond their original territories. The young forests of Archaeopteryx, with their extensive roots and easily transported spores, benefited from the floods to expand. These events thus contributed to the spread of flora and the transformation of terrestrial ecosystems. In some regions, a marked botanical renewal can be observed, with increased diversity on freshly enriched soils. The combination of violent tsunamis and the appearance of new plants plays a key role in large-scale evolution. Ancient coastlines, once covered with algae and bacterial mats, saw the arrival of vascular plants capable of stabilizing soils and trapping sediments. Their roots form a dense network that slows erosion and initiates wetland formation. This vegetation supports the establishment of invertebrates and vertebrates, transforming shores into refuges conducive to the expansion of terrestrial life. In the Silurian and Devonian periods, the exchanges between sea and land became increasingly complex, fueled by the rise of the first forests and the force of tsunamis. The alternation between calm periods and brutal submersions shaped a contrasted landscape. The fossils buried in the sediments of this era tell the story of worlds in transition. It is the story of pioneering ecosystems under construction, but also of sudden, violent, and sometimes devastating events that mark the dawn of life on land. Recent discoveries refine our understanding of this key period every day. By studying formations like the Murrendal Group and the tsunamis caused by the Silurian and Woodley impacts, researchers are gradually reconstructing the coastal landscapes of the Silurian and Devonian. They compare deposits, analyze strata marked by waters, and trace the tracks left by aquatic fauna. Each advance reveals how life adapted, evolved, and strengthened in the face of upheavals. This period also marks profound tectonic and climatic changes. The rise of mature forests, like those of Archaeopteryx, altered the atmosphere. By absorbing large amounts of carbon dioxide, these plants enriched the soils with organic matter. Gradually, the climate cooled, although tropical areas maintained exuberant flora and fauna. These new, still unstable equilibriums paved the way for the future evolution of plants, and notably, for the emergence of the first vertebrates capable of living on land. Soon, these forested shores would see the emergence of more audacious life forms. Plants continued their advance on land, while lobe-finned fish began the great transition towards walking. Between 359 and 252 million years ago, Earth underwent a decisive phase, the Carboniferous, followed by the Permian. During this long period, the planet changed radically due to glaciations, tectonic movements, and intense volcanic activity. The continents, then arranged very differently, experienced extreme variations in sea level and climatic upheavals. Two major events marked this interval: the extension of vast polar ice caps over Gondwana and the formation and subsequent collapse of large coal basins. Finally, towards the end of the Permian, the gigantic eruptions of the Siberian traps further disrupted the climate. In this chapter, we will see how ice, volcanoes, plates, and landforms influence the dynamics of both marine and lacustrine tsunamis. To understand this period, one must first visualize the global context. Gondwana combined present-day Africa, Australia, India, Antarctica, and South America. In places, it was covered by thick ice caps, comparable to those of Greenland or Antarctica today. Under climatic variations, these ice masses thickened or melted, abruptly changing the pressure exerted on the Earth's crust. This phenomenon, known as glacio-isostasy, caused the ground to sink under the weight of the ice and then rise when it disappeared, like a piece of wood freed from a weight. Sometimes, these movements triggered sudden collapses, releasing immense quantities of water, ice, and sediments into lakes or seas. These collapses then caused waves comparable to tsunamis, fueled by the massive fall of ice or the rupture of glacial water reservoirs. In the Carboniferous, the equatorial zones, warm and swampy, housed vast forests that would give rise to thick layers of coal. Meanwhile, further south, Gondwana was periodically covered by ice. The climatic contrast was striking, with up to 30 degrees in the tropics and well below zero at the poles. The ice mass of the southern Gondwanan caps varied according to climatic cycles. When it became too heavy, it depressed the Earth's crust. Then, by partially melting, it caused a rapid rebound of the ground, leading to sudden floods, violent flows, and the formation of proglacial lakes located in front of glaciers. When an ice barrier gave way or a valley collapsed under pressure, the released water turned into a torrent. This outpouring could generate a tsunami, sometimes in a lacustrine environment. At the edge of the southern Gondwanan ice caps, rapid melting could flood entire valleys. Rivers, loaded with water and debris, overflowed suddenly. The water then rushed into closed basins or reached the ocean in a very short time, generating enormous waves. To find traces of these, scientists analyze layers of rocks called tsunami-ites. These layers can be recognized by their chaotic textures, coarse grains on the surface, unsorted deposits, inverted structures. In the glacial context of the Carboniferous Permian, these deposits reveal massive and sudden water surges caused by the collapse of glacial masses. During this period, South America, Australia, and part of Southeast Asia formed a single block. Vast basins, such as those of Sydney or Paranah, accumulated immense quantities of plant debris, future coal deposits. These coal basins gradually sank under their own weight, a phenomenon called subsidence. But sometimes, this subsidence accelerated abruptly due to tectonic tensions. Imagine a swamp rich in organic matter collapsing by several meters. Water then rushes into the depression, generating an internal wave that propagates within the basin or toward a nearby sea. In shallow seas covering the continents, these waves can sweep across vast areas. They are sometimes mistaken for tsunamis. In the deposits, researchers find clear clues: folded coal layers, tilted sediments, marks of a sudden disturbance. Towards the end of the Permian, around 252 million years ago, a cataclysmic event shook the planet. It was the gigantic eruption of the Siberian traps. The word trap, of Swedish origin, means staircase, referring to the stacked lava flows covering millions of square kilometers. This extreme volcanism released massive columns of magma to the surface, accompanied by gases such as water vapor, carbon dioxide, and sulfur compounds. Part of this activity may have occurred under thick ice caps. In this case, the heat rapidly melts the ice, causing torrents of water. If the magma chamber empties suddenly, it can lead to a collapse, a caldera, and release this water abruptly, triggering a volcanic tsunami. Even though direct evidence is lacking, many clues suggest that such waves could have hit the coasts hard, disrupting life even inland. In the rocks from the end of the Permian, geologists often identify clues called combined sedimentary traces. Among them are drop-up clasts, which are rock fragments deposited where they shouldn't be found. Imagine a large rock in the middle of a layer of very fine sediments. It was probably transported by ice or by an extremely powerful current. Sometimes, it even seems to move upstream against the natural sorting of grains. This type of structure, accompanied by marked erosions or isolated pebbles, indicates a violently disturbed environment, often linked to a tsunami, rather than a simple marine deposit. Geologists also identify what are called ravaged paleosols, ancient fossilized soils formed under specific conditions, then abruptly eroded by an intense current or wave. Only sparse traces remain, testifying to a violent episode. There are also reworked coal intercalations, remnants of plants partially transformed into coal, normally deposited in calm swamps. But when a tsunami lifts and redeposits them, they mix with other materials, coarse sand, marine clay, rock fragments. This chaotic mixture in a single layer is a key clue. It reveals a sudden, powerful event, comparable to a tsunami. The combination of these clues leaves little doubt. Certain events at the end of the Carboniferous and the Permian were of extreme violence. Glaciations, volcanoes, and tectonic movements disrupted coastlines, but also inland areas. Huge waves, several tens of meters high, submerged entire regions, crushed entire forests of tree ferns, and displaced flora and fauna over vast distances. The ecosystems of the time were hard hit. The seabeds were also shaken, reefs destroyed, habitats buried, biodiversity swept away. And to this are added climatic upheavals linked to rising seas, massive eruptions, and the reorganization of continents. Orogenesis, the formation of mountain ranges, also plays a major role. During the Carboniferous Permian, several massifs emerged, such as the Hercynian chain in Europe, born from the collision between continental blocks. These reliefs erode and release enormous quantities of sediments into neighboring basins. Transported by rivers, this material accumulates on the margins of the continents, sometimes stably, sometimes in a precarious balance. When the slope becomes too steep or a tectonic shock occurs, an underwater slide can be triggered, generating a destructive wave. Although better documented in other eras, these slides also occurred in this period, as evidenced by certain avalanche deposits from the Carboniferous Permian. At the end of the Permian, Earth experienced the greatest extinction in its history. Indeed, thousands of marine and terrestrial species disappeared. This cataclysm resulted from a chain of factors: abrupt climate change, ocean acidification, a drop in marine oxygen, massive volcanic eruptions, and rapid sea level changes. Tsunamis by overwhelming coasts and seabeds likely worsened the situation on a local scale. Fossils found in reworked coal layers bear witness to these violences. Even if they were just a link in the disaster, these events reveal how vulnerable ecosystems were. At this critical moment, While mammalian reptiles and ancestors of dinosaurs were beginning to diversify, the tsunamis may have also reshaped the paths of evolution. Some tsunamis altered the climate, geography, and distribution of life. Imagine vast forests of lycophytes or tree ferns, the dominant plants of the Carboniferous, swept away in an instant. Uprooted, transported, and then deposited elsewhere, these plant masses decompose, enriching the soil, but also disrupt the biogeochemical cycles. Rapidly buried, some escape oxidation, forming the coal deposits that would later fuel human civilizations. At sea, these waves deposit sediments that favor some species but smother others. For scientists, these traces reveal how brief but intense catastrophes profoundly shaped the evolution of life on Earth. Today, geologists study deposits in South America, Australia, Antarctica, or South Africa. By analyzing the nature of sediments, their arrangement, or the presence of atypical elements like isolated stones and coal layers, they retrace history, layer by layer. Using computer models, they simulate the propagation of waves on a partially glaciated continent. The collapse of a coal basin or the disintegration of an ice cap under the magma's effect are scenarios studied, and the results converge. Waves several tens of meters high could indeed have swept across these ancient landscapes, rivaling the largest tsunamis in modern history. The Carboniferous Permian is one of the most turbulent periods in Earth's history. Between glaciations, mountain formations, and volcanic outbursts, coastlines were continually transformed. Marine or lacustrine tsunamis struck these landscapes violently. The strata bear the traces of these events. Shattered rocks, uprooted forests, shores devastated in an instant. This natural chaos intermingled with the rise of dense forests, the emergence of new chains of animal life, and a world in constant mutation, far removed from our current geographical landmarks. This vast array of data reminds us how sensitive ancient landscapes were to climate variations and tectonic forces. The cyclical ice caps of Gondwana, ground tilting, the formation or rupture of vegetated basins, and the gigantic eruptions of the Siberian traps created conditions conducive to tsunamis of exceptional magnitude. By studying drop-up clasts, ravined paleosols, or disturbed coal layers, researchers retrace this tumultuous history. Everything in the Carboniferous Permian geology reveals a world shaped by ice and fire. Uplifts, collapses, and waves carved landscapes whose traces, still visible today, tell a never-ending cycle of creation and destruction. Understanding the Carboniferous Permian tsunamis also means gauging Earth's capacity to transform, then and now. The collapses observed on the fringe of today's Antarctic ice caps are lesser echoes of those that struck Gondwana. The ruptures of natural dams in the modern Alps are reduced echoes of past catastrophes, once at the scale of continents. In Iceland, certain volcanic eruptions melt glaciers, causing sudden floods called Jökulhlaups. The scenery has changed, but the mechanisms remain. Whether climatic, volcanic, or tectonic, when a factor disrupts the balance, moving water becomes a force capable of reshaping everything. This lesson in geological history reminds us that certain natural mechanisms endure through the ages. Whether in the Carboniferous Permian period or today, the Earth operates according to the same dynamics. Caps that collapse, basins that give way, magma that erupts, and the sea that sometimes reacts within minutes. Tsunami after tsunami, these events leave their marks in sediments, rocks, and fossils. they can isolate species, or, conversely, disperse them. Each giant wave shapes barriers or corridors, redrawing ecosystems. And with each upheaval, life adapts. This is how evolution progresses to the rhythm of chaos. When scientists study the geological layers dating back 252 million years, they find traces of a major volcanic cataclysm occurring in an already tumultuous context of marine and glacial variations. Samples from northern Russia or the ancient margins of Gondwana reveal a mixture of basalt, ash, carbonaceous debris, and disrupted deposits, signs of sudden floods. Earlier, in the Carboniferous, some coal veins formed after the sudden submergence of wet forests, buried under layers of clay or sand. All this evidence shows that tsunamis played a key role. In this world in motion, amid forming mountains, colliding plates, and expanding forests, water has often been the catalyst for change. Today, the study of paleo-tsunamis reminds us that Earth has never been still. Between 359 and 252 million years, it was sculpted by tectonics, climate, and volcanism, offering a vast stage to the most destructive forces. These events shaped continents, basins, and ecosystems, paving the way for future eras. We often associate tsunamis with modern earthquakes, but geology reveals much more varied origins. The Carboniferous Permian period provides a striking illustration. These ancient waves disturbed ecological balances, left records in the rocks, and posed questions for researchers. Their vast and slow history contrasts with our focus on just a few decades. Yet, by studying them, we understand our place in Earth's long timeline a little better. The Triassic period, spanning from 252 to 201 million years, marks the aftermath of an unprecedented crisis. This refers to the mass extinction at the end of the Permian, which swept away much of life on Earth. In this unstable world, shaken by geological upheavals, the continents united into a single mass begin to fragment. Faults, rifts, and new shallow seas appear, while volcanic activity remains intense, particularly around Tethys. It is in this ever-changing landscape that massive waves, mega-tsunamis, emerge, and life attempts to reclaim the devastated coasts. To understand this era, one must explore major phenomena like the Karoo-Ferrar volcanic outpourings, the Paleo-Triassic rift earthquakes, the impact of Manicouagan, or the role of dicroidium flora on soil stability. We begin this journey with the mega-tsunamis linked to the magmatic provinces of Karoo and Ferrar. Karoo once covered a large part of southern Africa. Ferrar, on the other hand, extended to Antarctica and beyond. At the time, all continents formed a single supercontinent, Pangaea. Africa, South America, Europe, Asia, Australia, and Antarctica were joined. But in the Triassic, this unity begins to crack. Under the pressure of internal forces, Pangaea stretches, fractures. Rifts appear, gradually paving the way for new oceans. The basalt cliff guardians refer to immense natural walls formed by the accumulation of lava flows rich in iron and magnesium. These volcanic layers stack up, creating vertiginous walls, sometimes hundreds of meters high. They are found around the ancient Tethys Sea, which separated the north and south of Pangaea. But under tectonic pressure and the weight of the rocks, these cliffs sometimes suddenly collapse, releasing colossal energy. Imagine a gigantic basaltic cliff, massive, seemingly solid, but eroded from within by invisible fractures. Then suddenly, an entire section detaches. Millions of tons of rock plunge into the sea. The impact triggers an extremely violent wave, a mega-tsunami. According to recent simulations, these waves could reach several tens, sometimes even hundreds of meters in height, submerging coastal areas for kilometers. Mega-tsunamis in the Karoo-Ferrar are born from gigantic volcanic landslides. When millions of tons of rock suddenly collapse into the sea, the impact generates a wave that propagates at high speed. The run-up refers to the maximum height reached by this wave upon reaching the coast. In the case of the Triassic, it could be so high that entire portions of the coastline would disappear underwater. Sediments were torn away, shorelines reshaped, and local life swept away in an instant. In parallel with these spectacular collapses, the Triassic is also marked by the existence of a system of faults and fractures referred to as the Ethiopian Paleotethys, to evoke an ancient rift situation in this area. At the time, tectonic plates began to move, outlining the beginnings of an ocean opening. Earthquakes were relatively frequent because the crust was slowly fracturing under the effect of accumulated stresses. When an earthquake strikes at sea or near the coast, it can trigger a tsunami. It suffices for the seabed to lift or sink abruptly, even if only by a few meters, to displace millions of tons of water in an instant. A wave then forms and speeds in all directions. In the Triassic, some earthquakes in the region of the Ethiopian Paleotethys Rift likely triggered tsunamis capable of reaching the shores of the young Indian continent. Models suggest an impressive run-up between 40 and 60 meters in height at impact. A wave of 40 to 60 meters is a wall of water as high as a 15-story building, rushing in at several hundred kilometers per hour. When it hits the coastline, everything gives way. Vegetation is torn out, sediments carried off, coasts redefined. The landscape becomes unrecognizable. The force of the water scatters plants and animals over kilometers. Some marine creatures end up being projected far inland. Coastal plants, if they survive, are displaced and disseminated, sometimes forming new ecosystems. In this tumultuous geological context, a question arises: how was coastal plant life able to show resilience? It's important to know that the end of the Permian and the dawn of the Triassic were periods of great suffering for ecosystems. Despite the magnitude of the disasters, some plant lineages managed to persist, then regain dominance by taking advantage of successive natural rebuildings. Among them is a group of seed ferns collectively known as Dicroidium. Dicroidium is very widespread in the Triassic in the southern hemisphere. These plants are recognized by their large-lobed and alternate leaves. After the Permian crisis, they quickly colonized coasts and plains, taking advantage of devastated environments. Their strong roots helped stabilize moist soils, playing an important role in ecosystem reconstruction. When a tsunami hits, it brutally tears out vegetation. But in the following weeks, some organic remnants such as spores, seeds, or fragments of roots can be transported by marine and river currents, then deposited in areas conducive to regeneration. Paleopalynological analysis, i.e., the study of fossilized pollen and spores trapped in geological layers, reveals that after many Triassic tsunamis, traces of Dicroidium are found above the characteristic deposits. This observation suggests rapid plant recolonization. Thanks to paleopalynology, scientists can trace the recolonization of plants on disturbed sediments. Marine or lacustrine deposits displaced by a tsunami sometimes contain pollen grains or spores that escape destruction. Once the water recedes, these elements fall on bare soil, ready to welcome new growth, especially if the climate remains warm and humid. The Triassic was a generally hot period, with temperatures often exceeding 30 degrees in the tropics. Although higher altitude or more southern areas experienced variations, this warmth largely favored plant regrowth. To measure the power of Triassic tsunamis, we can mention the Manicouagan impact, which occurred about 200 to 15 million years ago. This event left one of the best preserved meteorite craters in the world, the circular Manicouagan Reservoir located in eastern Canada. At the time, this area belonged to the Laurentian supercontinent, which encompassed much of present-day North America, as well as Greenland. When an asteroid or a comet collides with the Earth, the energy released is immense. The impact can melt and vaporize rock, creating a crater tens of kilometers long. During the Triassic period, when the climate and ecosystems were already unstable, an impact of this magnitude could exacerbate the imbalances. But a question arises: how can such an event trigger a tsunami? When an asteroid hits a continental region, the detonation throws vast amounts of shattered rocks into the air. But if it strikes a coastal area or shallow waters, the impact can generate a tsunami. In the case of Manicouagan, the term circum-Laurentian tsunami is used because the waves would have radiated around the Laurentian craton. This craton is an ancient, very stable continental core, around which other fragments of Earth's crust have added over time. Models show that a wave generated by an impact can travel thousands of kilometers, cross seas, and strike distant shores. The phenomenon of retro-coastal erosion describes how coastal sediments are ripped away by the force of the retreating water after having carried significant deposits onto land. In the southern Appalachians, then located on the flank of the Laurentian craton, evocative geological clues are found: disrupted layers, poorly sorted conglomerates mixed with organic debris, or fissures filled with recent sediments. The impact at Manicouagan is, of course, not the only element to have shaped the Triassic landscape. The initial rifting movements of Pangaea, continuous volcanic activity, and climatic variations also played a key role in the formation of landforms and ecosystem evolution. But by focusing on tsunamis and the transformations of coastal areas, one can more clearly perceive the extent of the upheavals that affected the fauna and flora of this time. The Triassic marks the emergence of the first dinosaurs, still small and not very diversified, but already present on land. In coastal areas, marine reptiles like ichthyosaurs and nothosaurs struggle to cope with tsunamis. Some attempt to dive deep to escape the wave, but the brutality of the surge, the sediment agitation, and the violence of the water often render these attempts vain, if not fatal. A fascinating question is to assess the damage a megatsunami could inflict on a continental scale. For this, paleontologists and geologists study precise sedimentary indicators, such as chevron laminations that indicate strong currents, or debris beds where the coarsest elements are found on top, a sign of sudden deposition. Each new site revealing these structures enriches our understanding of past water movements. Although they were devastating, Triassic tsunamis could also, in the long term, encourage the dispersal of species and the creation of new habitats. As the waves retreated, they left behind shells, invertebrates, and microorganisms, capable of recolonizing lagoons or wetlands. The churning of marine sediments temporarily enriched these environments with nutrients, thereby boosting biological productivity in newly submerged areas. It would be excessive to believe that tsunamis alone shaped all Triassic shorelines. Seasons, climate, river floods, and landslides also continuously contributed to reshaping coasts. Ordinary erosion and sedimentation processes continued, but when a mega-tsunami struck, it transformed everything in a few hours. Each wave imposed a new survival challenge on coastal species. Earth managed to overcome the Triassic's successive crises thanks to the resilience of life. Despite the mass extinction at the Permian boundary, which wiped out a large part of marine species, the survivors managed to exploit new spaces. Dicrodium forests, for instance, regenerated on young soils enriched with minerals. Insects, essential for pollination, also quickly recolonized these open environments, contributing to the reconstruction of ecosystems. The reconfiguration of the coasts during a rifting, like the one observed in the Ethiopian region in the Triassic, favored the emergence of new ecological gradients. Between the sea and the continental hinterland, estuaries, deltas, and swampy areas comparable to mangroves formed. Although modern mangroves are based on contemporary plants, analogous plant communities already existed, adapted to intertidal environments. They had to develop strategies to withstand variations in water levels and salt intrusion. The emergence of new coastal environments directly transforms ecosystems. Primitive amphibians, small reptiles, and other semi-aquatic animals colonize these more productive zones. Rivers deposit fine sediments that enrich the soils, allowing new plants to settle. Thus, despite the persistent threat of tsunamis, life manages not only to survive, but sometimes even to gain in diversity. Let's return to the impact of Manicouagan and the Circumlaurentian tsunami. On a geological scale, it remains difficult to assess the frequency of extraterrestrial impacts. But with each such event, the shockwave spreads over hundreds of kilometers. On the margins of the Laurentian craton, the combination of shock, seismic tremors, partial vaporization of water, and the collapse of rock blocks into the sea could have generated several successive waves, each reaching impressive heights. When these waves strike the southern Appalachians, they erode sedimentary formations hundreds of thousands of years old. Retrocoastal erosion refers to the retreat of water towards the sea, often in several phases. The wave advances, tears away materials, deposits them further, then retreats taking other sediments with it. These back-and-forth movements leave clear traces, layers of silts, clays, and pebbles mixed chaotically, visible signs of the violence of the current. This type of deposit is recognized in some geological formations thanks to specific clues: fragments of marine organisms mixed with continental sediments, upward-oriented fissures filled with coarse materials, or rock blocks from afar, moved by the power of the waters. All these elements testify to rare and violent processes, characteristic of brutal events that have durably marked the landscape. Today, megatsunamis are rare, but their study through geological times shows how greatly interactions between land and sea have influenced the evolution of life. The Triassic is not just a period of reconstruction after massive extinction. It is also a major turning point where new forms of life emerge, laying the foundations for the great kingdoms of the Jurassic and Cretaceous. Looking at the Triassic as a true leap in time reveals an Earth in full rebirth. On the lands now cleared by the wave, some plant species emerge strengthened from these trials, taking advantage of light, heat, and the presence of water to flourish again. As the map of future existence gradually takes shape, the ancestors of dinosaurs braved these often unstable environments. Marine reptiles, still adapted to aquatic environments, must deal with the threat of tsunamis, capable of projecting them out of their original habitat. Yet, it is likely this alternation of catastrophes and opportunities that allowed the biodiversity of the late Triassic to experience a notable expansion in certain ecological niches. The Middle and Upper Triassic indeed see the emergence of numerous groups of reptiles, plants, and insects. In the background, the impact of Manicouagan stands out as a geological punctuation, a spectacular reminder of the fragility of life in the face of cosmic forces. The Triassic is a period of renewal and upheaval. After massive extinction, new species colonized the ever-changing coastlines. The Mega-Tsunamis linked to the Karoo-Ferrar volcanic provinces, the earthquakes in the Ethiopian region, and the expansion of dicroidium forests reflect the dynamic shores of the time. The real lesson is not just in remembering past events, but in life's ability to be reborn. After each destruction comes a rebuilding phase. Coastal areas, constantly upheaved, are places of intense interaction between sediments, water, and life. Beaches erased, estuaries displaced, ferns swept away. Yet life persists. It adapts, reappears where it's least expected, and continues endlessly to reinvent itself. This is a tale of perpetual reconstructions, dictated by the movements of tectonic plates, volcanic collapses, asteroid impacts, and climatic variations. Understanding the Triassic through these prisms means realizing just how much our planet has never stopped changing. The current scenery is just yet another temporary version, and the traces left by ancient mega-tsunamis are as many silent messages about the power of natural processes. The landscapes of 250 million years ago are partially accessible to us through dicroidium fossils, disturbed sedimentary layers, and large impact craters. A layer of sandstone, a cluster of fossilized pollen, or a fractured rock structure. Each of these clues composes the grand mosaic of the Triassic. Geologists, paleontologists, and climatologists cross their discoveries to gradually reconstruct this ancient and vanished world, still readable in the Earth's archives. Tectonic shocks and celestial impacts sculpt the reliefs, fragment Pangaea, and disrupt ecosystems. On the coasts, tsunamis become the scene of a constant struggle between natural forces and species adaptation. Engraved in the rock, these events remind us that Earth is a world in perpetual motion. Today, the distant echo of these mega-tsunamis reaches us in the form of inverted sediments, fossils carried away from their original biotope, pollen misplaced in unexpected layers. Current scientists, by studying these clues, trace the journey of collapsed basalt cliffs, faults marked by the violence of earthquakes, columns of volcanic ash deposited in a paleo-ocean. As for the dicroidium flora, it serves as a living proof of the tenacity of vegetation, capable of reinvesting devastated areas. Today, the name Manicouagan mostly evokes the large reservoir in Canada. By taking a moment to grasp this force, one discovers a harsh, unpredictable world, but also one that harbors new impulses. A world where life, despite the uncertainty of the elements, continues to survive, adapt, and sometimes even expand. All the elements we have just explored are linked to this complex and fascinating period known as the Triassic. Despite extreme conditions, earthquakes, eruptions, and an impact from the sky, life continued to reinvent itself. These gigantic waves, far from being solely destructive, contributed to redefining ecosystems. At the heart of this chaos, Dicroidium, a modest plant with no apparent defense, managed to assert itself and profoundly mark the fossil records, a striking testimony to the resilience of life through the ages. Imagine a vast marine and terrestrial world between 201 and 145 million years ago during the Jurassic. During this pivotal period, tectonic plates begin to move markedly, reshaping continents and oceans. The global climate is rather warm, with average temperatures ranging between 15 and 20 degrees Celsius, according to paleoclimatic estimates. Unlike today, the poles are not covered with ice. On the emerging lands, large forests dominated by conifers, tree ferns, and cycads thrive, alternating between wet zones and drier regions. In the oceans, fascinating creatures inhabit the waters. Ammonites, small mollusks with spiral shells, along with ichthyosaurs, marine reptiles with streamlined bodies reminiscent of modern dolphins, reign supreme. In this evolving geological and biological context, the opening of the Weddell Sea takes place, south of what will later become Antarctica. At that time, Antarctica is still connected to other continents, forming a vast landmass. However, the movement of tectonic plates creates deep fractures in the crust, allowing water to gradually flood into new oceanic basins. These fractures develop over millions of years under the influence of mantle plumes, columns of very hot rock rising from the Earth's mantle. They thin the crust and promote the formation of new marine basins. The opening of the Weddell Sea is thus accompanied by the appearance of oceanic ridges, long underwater volcanic chains where the crust forms and extends. However, the most striking geological phenomenon of this tectonic reorganization remains the collapse of the carbonate platforms located on the edge of Antarctica. These carbonates, comprised mainly of calcium carbonate, originate from the accumulation of marine debris as well as chemical processes in the ocean. In the Jurassic, thick layers were deposited on the Antarctic continental margins. But when the plate accelerated its movement and tectonic forces intensified, these structures became unstable. Large portions then broke off and plunged abruptly into the ocean. The sudden entry of these rock masses triggered immense tsunamis, projecting waves in concentric circles around the South Pole. One must imagine colossal water waves rising and rushing at a staggering speed. Even without precise measurements for this ancient event, it is estimated, based on modern cases, that these tsunamis could exceed 100 meters near the point of collapse. As they spread out, their energy dissipates over vast areas, creating what is known as circumpolar tsunamis in the southern hemisphere. The neighboring coasts, then inhabited by ecosystems adapted to a temperate climate, underwent violent disruptions. Swamp forests swallowed, sediments swept over kilometers. The coastal landscapes were profoundly reshaped. At the same time, further north, other tectonic movements triggered equally spectacular phenomena. On the North Atlantic margin, the future junction between Norway and Greenland, occurred a massive mega-gravity slide. This is a colossal collapse of rocks and sediments along an underwater slope. In this specific case, geologists estimate that more than 3,500 cubic kilometers of materials cascaded down the sea floor. To grasp the scale, it's as if several kilometers of sediment thickness suddenly detached from an area the size of an entire region. When such a slide occurs under the sea, the abrupt displacement of water causes new, powerful, and sudden tsunamis. At the Jurassic scale, these collapses can be triggered by violent earthquakes or by the instability of sedimentary layers saturated with water, ready to give way at the slightest jolt. On the North Atlantic margin, the separation between the Eurasian and North American plates creates a context conducive to this type of catastrophe. The consequences on coastal fauna are significant. Low-lying areas quickly become submerged, severely affecting marine grasslands and communities of invertebrates living on the seabed. To trace these events, one must dive into the sedimentary archives, the rock layers deposited at the ocean floor and preserved to this day. In Argentina, the Inoceramos Formation is a striking example. It is named after the inocerams, fossil oysters abundantly found in the rocks of the era. Upon examination, one discovers undulating layers, strata forming marked waves, signs of intense currents. There are also antipodal laminations, where thin layers alternate their orientation, revealing rapid current variations. Finally, floating grains, large particles trapped in a fine matrix, attest to a turbulent transport before the final deposit. The analysis of these structures reveals that rare but extremely violent events disturb the regular sedimentation of this region of Argentina. Among the possible causes, tsunamis appear to be the most probable. Their powerful waves displace sediments of all sizes over long distances. The undulating layers and inverted laminations indicate a shallow marine environment, shaken by successive flows constantly altering the current. It can be challenging to distinguish the traces left by a sedimentary storm from those of a tsunami, but here, the sudden intensity of the event clearly argues in favor of a tsunami. For the marine life of the time, these upheavals had contrasting effects. Ammonites, thanks to their dispersal capacity, sometimes benefited from the nutrients brought back into suspension by the tsunami. This stimulates plankton production, temporarily enriching the food chain. After the initial shock, some coastal areas repopulate quickly, as evidenced by layers rich in ammonite fossils in the geological strata. These creatures manage to reclaim space, proving their remarkable resilience. Ichthyosaurs, large marine reptiles adapted to swimming, are also affected. Although they live far from the coasts, some can be injured or trapped by the force of a tsunami, but thanks to their mobility, they quickly flee troubled areas and sometimes take advantage of ecological changes to explore new territories. Their ability to move enables them to recolonize disturbed habitats, unlike benthic species, which are more sedentary and bear the full brunt of the impact, struggling to recover. In biogeographical terms, meaning the distribution of living beings on Earth, Jurassic tsunamis may have driven certain species to migrate over long distances. Natural rafts of vegetation, trunks, roots, and debris carried by the wave could transport small animals like insects or vertebrates to other shores. Even though this phenomenon is poorly documented for the Jurassic, it undoubtedly contributed to the dispersion of many species. By altering coastal landscapes and opening marine pathways, these events also promote genetic exchanges between isolated populations, influencing long-term evolution. In the Jurassic, the fragmentation of continents is accompanied by the emergence of oceanic ridges and powerful mantle plumes. These phenomena are not mere details for geologists. They are the deep drivers that redraw the world map, alter oceanic currents, and transform coastlines. The earthquakes they trigger can generate tsunamis, traveling thousands of kilometers. In this context, the carbonate platforms of Antarctica, or the North Atlantic margin, become risk zones, prone to collapses or massive slides. To understand these upheavals, geologists rely on seismic mapping, drilling, and the analysis of ancient rocks. In Argentina, the Inoceramos Formation is a veritable open book on this tumultuous era. Wavy strata, inverted laminations, floating grains are all traces left by the passage of giant waves. These clues reveal how the sea suddenly invaded the coasts, carrying away sediments and debris, before retreating and leaving an inverted sedimentary geometry. For many, it is hard to imagine how profoundly these events shape species distribution and influence marine evolution. And yet, each collapse, each tsunami, each deposit gradually transforms the landscape and ecosystems, sometimes for millennia. Ecologically, these tsunamis strike without warning. In an instant, they destroy primitive coral reefs, coastal forests, and estuaries teeming with life. Yet, a recolonization dynamic quickly sets in, especially among species capable of great migrations like ammonites or ichthyosaurs. The nutrients released by the wave, combined with the vacant niches, provide fertile ground for their expansion. In this brutal cycle of destruction and renewal, nature sometimes turns chaos into a driver of adaptation. In the long term, these tsunamis reveal the power of Earth's internal forces. By weakening the crust, mantle plumes pave the way for new oceans, but also make certain areas unstable. The Jurassic perfectly illustrates the close link between geology and biology. The opening of a sea results from deep activity, but disrupts coastal ecosystems on the surface. Antarctic collapses or North Atlantic slides are not mere local incidents. They contribute to the global reconfiguration of the planet, influencing species evolution on all scales. The Jurassic, often perceived as a peaceful era inhabited by dinosaurs, was actually a world in constant upheaval. Tectonic plates were actively drifting, causing faults, underwater volcanoes, and oceanic mixing. Sea levels were constantly changing, exposing and then submerging continental shelves. In the midst of this turmoil, tsunamis reminded us of the brutal force of Earth's mechanisms. For the fauna, these giant waves disrupted ecosystems. Breeding sites were submerged, others appeared, altering the balance of food chains. At its core, these great tsunamis teach us an essential lesson. Life knows how to bounce back, even after the worst catastrophes. Ammonites, with their spiral shells, managed to float, move, and recolonize the seas. Ichthyosaurs, agile and powerful, maintained their presence while settling on new shores, freed from competition. As for plants, spores and seeds carried by the waters gave new life to the emerging lands, wherever the soil offered an anchoring point. The resilience of life, once again, prevails. Some researchers believe that periodic catastrophes favored the sustainable distribution of marine fauna across the Jurassic world. Others see it as a driver of evolution. Indeed, a tsunami isolating a population can create conditions for the emergence of a new species, evolving far from its original group. To imagine a Jurassic tsunami, picture a furious ocean, raising immense waves, crashing onto continents in the midst of breaking apart. Marine reptiles flee the turmoil, fish are hurled towards the shores, and entire sections of forest break away under the force of the water. Then comes the calm. The sea retreats, leaving behind chaos of gravel, broken shells, and fine sediments. These deposits, frozen in successive layers, retain the brief but powerful imprint of a cataclysm that will mark the Earth for millennia. The Jurassic shows us that the Earth has always been in motion. Tsunamis have shaped the coasts and seas repeatedly. In Argentina, the Tōhoku Formation bears witness to this, etched in the rock. Yet, at the heart of these upheavals, life persists, proving that even the worst cataclysms sometimes become the starting point of a new breath. The Cretaceous, between 145 and 66 million years before our era, marks a period of profound upheaval for the Earth. The climate, dominated by a powerful greenhouse effect, led to temperatures much higher than today, without lasting polar ice caps. The oceans housed shallow, warm seas and vast interior marine expanses. The continents, for their part, were covered with dense vegetation, composed of large ferns, conifers, and the first complex woods. It is in this lush environment that countless dinosaurs lived, from agile predators to immense herbivores in herds. Despite its bountiful biodiversity, the Cretaceous also experienced major catastrophes like the island arc Mega-Tsunamis. These gigantic waves, triggered by earthquakes or collapses in volcanic zones, originated where an oceanic plate slid under another, forming volcanic island arcs. The energy released in these regions generated waves capable of traveling hundreds, even thousands of kilometers. And when they hit the shores, they could reach several tens, sometimes hundreds of meters. In the tropical and temperate seas of the Cretaceous, these tsunamis undoubtedly left a lasting imprint. Among the most significant events at the end of the Cretaceous is the Chicxulub impact, 66 million years ago. An asteroid or comet, several kilometers in diameter, crashed into what is now the Yucatán Peninsula in Mexico. The energy released triggered a massive earthquake, followed by a sudden displacement of ocean waters. The resulting mega-tsunami would have exceeded a kilometer in height. Much higher than modern tsunamis, this titanic wave illustrates the extreme violence of the event. To measure the extent of the Chicxulub mega-tsunami, scientists rely on geological traces called tsunami-ites. These deposits have been found as far as Texas, in the Dakotas, and even on the coasts of Morocco. The wave crossed entire oceans, proof of its colossal power. By comparing sedimentary layers, researchers have shown that the impact altered the shape of coasts and disrupted the distribution of species, at least locally. Beyond its magnitude, the Chicxulub mega-tsunami caused major ecological upheavals. When hitting the coasts at full speed, the wave destroyed vegetation, tore up sediments, and engulfed low-lying areas. As it retreated, it carried tons of debris into the sea: vegetation, carcasses, organic matter. This mixture altered the chemistry of the seabeds and left deposits that sometimes fossilized. In shallow areas, muddy sediments could suffocate entire ecosystems. Chicxulub is not the only Cretaceous cataclysm. The collapse of the Ontong Java Plateau, one of the largest underwater volcanic structures, would have also generated waves on a Pacific scale. This plateau, born of massive eruptions, spanned millions of square kilometers. According to researchers, a part of it suddenly gave way, displacing immense volumes of water. The collapse would have also released torrents of sediments, known as turbidity currents. They can rush down the seafloor at high speed. This dual phenomenon would have caused giant waves, traveling thousands of kilometers to distant shores. Such collapses have a profound impact on the seas. When immense volumes of sediments are released, they smother benthic fauna and disrupt the entire ecosystem. Corals, which depend on clear water, can be suffocated. Fish, invertebrates, and other marine species find their habitat disturbed. Some migrate, others disappear. This imbalance can durably alter marine biodiversity and ocean circulation. Long before the Chicxulub impact, another event occurred in the early or middle Cretaceous, in the area of the present-day Norwegian Sea. It is believed to be an ancient landslide, nicknamed Storega Proto, precursor of the large slides that happened much later. According to geologists, huge sediments would have given way on the Norwegian continental margin, pushed by tectonic activity or the weight of deposits. This sudden movement under the sea would then have displaced large masses of water, triggering a tsunami. The exact height of the waves caused by the protostorega is unknown, but based on more recent slides in the same area, they could have reached several tens of meters. In the Middle Cretaceous, the shores were very different from today. Continental drift and interior seas strongly influenced the trajectory of the waves. To understand the impact, researchers reconstruct the paleogeography of the time through seismic surveys, marine drilling, and analysis of geological layers to estimate the volumes of displaced sediments and the power of the tsunamis. Whether it is Chicxulub, Ontong Java, or the slides in the Norwegian Sea, the central question remains: what impact on life? The Cretaceous hosted rich marine fauna, mosasaurs, plesiosaurs, ichthyosaurs, and reefs teeming with corals, calcareous algae, colorful fish, and crustaceans. On the coasts, forests of conifers and ferns sometimes housed dinosaurs. When a tsunami submerges such an ecosystem, it causes an immediate shock to all species, unable to flee or dive deep. In the long term, a mega-tsunami can cause massive erosion, carrying away fertile soils and destroying coastal habitats. Sometimes, sediments deposited offshore, rich in minerals, stimulate the growth of plankton and algae, temporarily reviving the food chain. But in other cases, the load is such that it suffocates life on the seafloor. It is therefore difficult to paint a single picture, as effects vary with context. One thing is certain, however: for coastal life, the shock is brutal. The fate of coastal dinosaurs in the Cretaceous intrigues researchers. Some herbivores, such as hadrosaurs, lived near the coasts and stood no chance against a tsunami. Trapped in saturated soil or submerged by the wave, many were swept away. Fossils sometimes show unusual dispersions, suggesting that bodies were transported over long distances. Paleontologists search for these clues in geological strata. Tsunamis of the Cretaceous also mark the plant landscapes. In the southern hemisphere, forests of Nothofagus, the southern beaches, covered regions such as Antarctica, Australia, or South America. When a wave struck these wooded coasts, it could uproot entire trees. Carried away by the sea, some eventually germinated elsewhere, promoting the dispersal of the species. These events influenced the distribution of these riparian forests, and sometimes the sudden disappearance of the vegetation cover allowed other plants to settle on the freshly reworked soils. Geologically, tsunamis leave a visible mark. Sometimes fossilized trunks are found far from their original forest, like the southern beaches. These waves act as giant conveyors, transporting roots, trunks, and pollens over long distances. By analyzing fossil plants and sediment layers, paleobotanists can gauge the violence of the event and its impact on the forests. A unique layer, rich in plant debris, reveals a brutal shock. Even pollen, trapped in lagoons, serves today to trace these forgotten cataclysms. The Cretaceous was a period of intense tectonic activity. Continents continued their drift, following the breakup of Pangaea. The Atlantic was widening, and volcanic arcs were forming in the Pacific and the Tethys Ocean. Earthquakes, eruptions, and giant slides were frequent, sometimes much more violent than those of today. In this context, mega-tsunamis were far from rare. Each major event could tip the balance of ecosystems, causing local extinctions of species unable to migrate or adapt. The first signs of instability in the Norwegian Sea during the Cretaceous already heralded a long series of landslides, which would continue into the Quaternary with the giant events of Storegga. These episodes also generated devastating tsunamis. This connection reminds us of an essential thing. The forces that shape the Earth are ancient, recurrent, and sometimes swift. In just a few minutes, they can redraw the surface of the globe with spectacular power. Mega-tsunamis often precipitated the disappearance of already fragile species that depended on coastal wetlands. Suddenly deprived of their habitat, many perished or did not survive the changes. The flora was also disrupted. The roots that stabilized the soils were torn away, giving way to erosion or other invasive species. These great marine catastrophes remind us that the Earth has never been static. In every era, upheavals disrupt an always unstable balance. In the Cretaceous, these phenomena followed one another in an already warm and greenhouse gas-saturated climate. This chaotic scene, punctuated by deceptive lulls, favored the adaptation of the most mobile and resilient species. Conversely, those that were too specialized often disappeared, unable to keep up with the rapid pace of change. In short, the Cretaceous perfectly illustrates how our planet combines tectonic forces to trigger giant tsunamis. The Chicxulub impact reshaped coastlines and left visible traces in sediments worldwide. The collapse of the Ontong Java Plateau reveals the instability of oceanic volcanic beds. As for the Proto-Storegga slide, it shows that fragile continental margins can also cause devastating waves. The Cretaceous, far from being peaceful, was an era of powerful upheavals. These titanic events, often relegated to mere details in geological history, nonetheless shaped the landscapes and distribution of life as found in the fossil record. Some forests, swept away by saltwater, managed to regrow differently. Decimated coastal species sometimes gave way to others better adapted. Studying these Cretaceous mega-tsunamis helps us today anticipate the consequences of future major shocks, like an asteroid impact or the collapse of an underwater volcano. For in reality, the Earth continuously alternates between creation and destruction, and giant waves have been one of its powerful instruments since the dawn of its history. The Paleogene, from 66 to 23 million years before our era, is a key period marked by a significant tectonic reorganization, climatic upheavals, and ecological transformations. The warm climate and the gradual isolation of Antarctica altered ocean currents, favoring powerful tsunamis linked to underwater landslides, volcanic collapses, or asteroid impacts. The coastal zones rich in biodiversity were deeply affected, while on continents, the rapid diversification of mammals shaped ecosystems. It is in this unstable and fertile context that several mega-tsunamis occurred, the traces of which still enlighten us today. About 55 million years ago, the ocean separating Australia from Antarctica was undergoing transformation with the gradual widening of the Tasman Strait, caused by the drift of continents. This tectonic extension weakened the sediment-laden continental slope, leading to massive collapses that triggered significant tsunamis in the young Antarctic basin. These violent events left their mark in formations called sedimentary breccias, composed of angular rock blocks mixed with fine particles, evidencing rapid and destructive slides. Ecologically, these tsunamis profoundly disrupted marine fauna, notably primitive fish, mollusks, and corals. They also reshaped coastlines, destroyed some coastal habitats, and forced vegetation to colonize new spaces, thus contributing to the evolutionary dynamics of coastal ecosystems of that era. About 45 million years ago, in the Caribbean basin, the proto-island of Montserrat experienced intense volcanism. The sudden collapse of a volcanic flank into the sea caused a massive underwater slide, generating a powerful tsunami. Amplified by the local geography, the wave traveled hundreds of kilometers, reaching distant shores. Corals, sometimes still alive, were found up to Cuba, attesting to the violence of the phenomenon. This tsunami caused a major shock to marine life. Indeed, fish, corals, and invertebrates were locally decimated, while submerged mangroves and coastal forests lost their vital habitats. In the Indian Ocean, the Deccan Traps testify to intense volcanic activity at the end of the Cretaceous and the beginning of the Paleogene. These eruptions, which began before the extinction of the dinosaurs, have durably transformed marine and coastal environments. The collapse of submerged calderas following the emptying of magma chambers generated significant tsunamis. The sediments of the Indian Basin bear these traces: poorly sorted grains, displaced layers, volcanic fragments at unusual depths. For marine fauna, the impact is severe. The habitats of sessile organisms are buried, and currents disperse eggs and plankton. On the coasts, waves submerge marshes and primitive palm forests, forcing a rapid reorganization of littoral ecosystems. About 35 million years ago, a series of meteoritic impacts struck the east coast of North America, the most famous being the Chesapeake Bay impact. These collisions released enormous energy, fracturing the Earth's crust and projecting debris into the atmosphere. The resulting tsunamis, sometimes in multiple waves, spread over vast distances, even reaching Europe. Coastal sediments retain the trace of these brutal waves, with chaotic deposits and breaks in stratification. The littoral fauna and flora then underwent major upheavals, with some species locally disappearing or migrating to new habitats. In the Paleogene, the slow separation of Antarctica from Australia and South America initiated the formation of new oceanic circulations, notably the future circumpolar current. The warm and humid climate favored the expansion of tropical forests to high latitudes. In this context, even a local tsunami can have devastating effects. The waves penetrate far inland, affecting terrestrial mammals that are still relatively immobile, while the burgeoning coral reefs become vulnerable to sediments and salinity variations. To understand the Paleogene Mega-Tsunamis, research relies on a multidisciplinary approach. Geologists analyze marine sediments through cores to identify ancient tsunami deposits. Paleontologists study the associated fossils to assess the impact on biodiversity, while geophysicists map underwater structures related to landslides or impacts. Through numerical modeling, wave dynamics can be simulated and compared to sedimentary data. Together, these disciplines help reconstruct these ancient disasters and assess current coastal risks. Throughout this research, international cooperation plays a central role. Teams from Europe, America, Asia, and Oceania share their samples and compare their observations. Every new discovery, even minor, completes the mosaic of events whose extent far exceeds human scales. The Paleogene thus reveals a dynamic past, sometimes brutal, but always fascinating. Ultimately, the study of Paleogene Mega-Tsunamis sheds light not only on our past, but also on the future of our shores and tomorrow. The Neogene, spanning from 23 to 2.6 million years ago, was a period of great geological upheaval. As continents continued their reconfiguration, immense instabilities resulted in several major tsunamis. Notable events of the Miocene and Pliocene include the giant Grand Bahama Slide, the Macran Canyon, the glacio-volcanic collapses of Antarctica. There's also the first phase of the Storegga Slide and the Messinian Crisis that nearly emptied the Mediterranean. Let's discover these fascinating episodes together to understand their origin, their impact on ecosystems, and how life reacted to them. The Miocene and Pliocene marked a major transition in Earth's climatic history. During the Miocene, temperatures were generally higher than today, favoring dense tropical forests and remarkable animal biodiversity, both on continents and in oceans. Vast grass plains stretched across temperate zones, populated by giant herbivores. The seas teemed with abundant fauna, including large sharks and primitive cetaceans. Gradually, the climate cooled, especially during the Pliocene, leading to the expansion of ice sheets and increased instability of the seafloor, conducive to the formation of mega-tsunamis. In this context of global changes, a spectacular event occurred in the Miocene. It was the gigantic undersea slide of the Grand Bahama Platform, known as the Mega-Slide. This region of the Bahamas rests on a vast limestone plateau, formed by the accumulation of marine debris, corals, algae, shells. Over time, these layers become unstable, especially on the flanks of the plateau. A tectonic imbalance or a sediment overload then triggers a massive collapse. Millions of tons of rocks and sediments rush down the slopes at high speed, suspending enormous quantities of calcareous particles. The abrupt displacement of this mass triggers a powerful tsunami, whose effects might have reached the coasts of Florida to the Yucatan. When huge volumes of sediment slide down a submarine slope, they abruptly displace the water column above, thereby generating a tsunami wave. This initial wave can propagate at several hundred kilometers per hour before losing intensity. Marine species living near the bottom can be swept away or buried under layers of displaced clay and limestone. On affected coasts, the impact is violent. The salt-resistant flora is often decimated, leaving room for recolonization by pioneer plants in subsequent years. This episode shows that even without an earthquake, the mere instability of submarine sediments can suffice to trigger a massive tsunami. The Macran Canyon, located in the Gulf of Oman off the coast of Pakistan, is an active tectonic area where the oceanic plate dives beneath the continental plate. During the Miocene, enormous quantities of sediments from continental erosion accumulated there, driven by sometimes wetter climates. These terrigenous deposits, piled up at the canyon's mouth, became unstable. When an earthquake shook the region, part of the seabed collapsed abruptly, triggering a giant submarine landslide. As in Grand Bahama, the landslide in the Macran Canyon mobilized a massive flow of sediments, rushing down the underwater slopes in the form of turbidites. This abrupt movement displaced a large mass of water, generating a potentially devastating tsunami. Chaotic deposits found in the Gulf of Oman confirm the magnitude of this event, sometimes referred to as the pre-Holocene tsunami. Coastal marine ecosystems, rich in mollusks, crustaceans, and fish, could have been severely affected, as well as the mangroves in the coastal plains of the time, close to the sea and vulnerable to flooding. The third event, about 15 million years ago, West Antarctica, still partially free of ice, experienced glacio-volcanic collapses. Under the ice shelves, volcanic activity generated heat and meltwater, causing increasing instability. A subglacial eruption, or an influx of water, could trigger the sudden collapse of a portion of the ice sheet. This type of phenomenon, releasing a mass of ice and water, was capable of generating regional tsunamis, disrupting the marine and coastal ecosystems of the southern hemisphere. An ice shelf is a vast expanse of ice floating on the ocean, an extension of the terrestrial ice sheet. When it collapses, it can suddenly release large amounts of water and ice, generating a tsunami. Cores taken from the Antarctic margins reveal chaotic deposits 15 million years old, containing fragments of rock and polished ice. These clues suggest a large-scale wave that disrupted marine ecosystems: seals, primitive whales, penguins, cold-water corals, and starfish. The Storegga slide, which occurred around 8 million years ago, marks the first major phase of instability of this submarine margin located off the coast of Norway. Long before the famous Holocene collapse, this area had already experienced major slides. During the Miocene, thick sedimentary deposits from continental erosion accumulated on the slopes in an active tectonic context. Variations in sea level and the initial glaciations in the northern hemisphere promoted the loading of these sediments, leading to a massive collapse of the continental slope. When the underwater slope became too unstable, a vast landslide occurred, moving enormous volumes of sediments and generating a tsunami. Seismic studies and sediment cores from the region reveal chaotic and reworked layers, contrasting with the irregular deposits of calmer periods. These traces suggest one or more major collapses during the Miocene. The waves could have reached the shores of Western Europe, disrupting coastal ecosystems. Even species well adapted to temperate climates could have experienced temporary disruptions to their reproduction or coastal habitats due to this event. The Messinian salinity crisis occurred around 5.9 million years ago, when the Mediterranean Sea almost completely dried up. The cause was tectonic movements that restricted the connection between the Atlantic and the Mediterranean via the Strait of Gibraltar. In a hot and dry climate, evaporation greatly exceeded water input, drastically lowering sea levels. The Mediterranean basin then transformed into a vast desert basin, where thick layers of salt and minerals were deposited. This abrupt transformation of the landscape disrupted aquatic fauna and coastal ecosystems, causing regional extinctions and massive migration of certain species. Simultaneously, marine life in the Mediterranean was largely decimated by the drying out. Only a few specialized species survived in hypersaline lakes or small residual seas. The former coastal areas, now emerged, were colonized by vegetation adapted to the saline and wet soils. These new lands favored the migration of many terrestrial species, notably herbivores such as gazelles, antelopes, or primitive elephants, which could move more freely in a profoundly transformed landscape. The aftermath of this crisis, known as the Zanclean Flood, marks the spectacular return of water to the Mediterranean. When the tectonic barrier at the Strait of Gibraltar gave way, the Atlantic Ocean rushed into the dried basin, triggering a rapid and massive filling. This spill, sometimes described as one of the greatest waterfalls in geological history, could have lasted from a few months to a few years. The water, rushing with extreme force, formed an initial giant wave capable of sweeping sediments, reshaping shores, and upheaving landscapes over hundreds of kilometers. The ecological consequences of the Zanclean flood were immense. Terrestrial species settled in the dry basin had to flee or disappeared under the massive arrival of saltwater. Plants tolerant of saline soils were swept away or buried under sediments. Conversely, marine species from the Atlantic took advantage of this new space to quickly recolonize the Mediterranean. Geologically, this event left very clear transgressive strata. These strata are layers where marine shells, foraminifera, and abruptly deposited sediments are found, witnesses to this flood as sudden as it was monumental. These catastrophes remind us how much the Earth is a system in perpetual motion. During the Neogene, fauna and flora had to adapt to an unstable environment shaped by tectonics, climate, and sedimentation. Marine mammals found new niches in reorganized seas, while coral reefs and coastal plants, often affected, managed to rebuild as soon as conditions allowed. Life, despite upheavals, never ceased to adjust. Throughout the Neogene, climate cooling and sea level variations accentuated the instability of continental margins. Thick layers of sediment, sometimes poorly compacted, slipped under the effect of seismic shocks or increased pressure from poor waters. Sometimes, the rapid accumulation of materials on already fragile slopes was enough to trigger collapse. Thus, areas like Grand Bahama, Macran, West Antarctica, Storegga, or the Mediterranean experienced massive slides, instantly releasing billions of tons of sediment and generating major tsunamis. These spectacular events bear witness to the cyclical and rebalancing functioning of our planet. The Miocene and Pliocene are no exception, leaving traces everywhere in geological records. Reworked sediments, chaotic breccias, or coarse sands, inserted into more regular layers, form a fascinating puzzle for scientists. As for the fossils of animals trapped in these deposits, they reveal both the brutality of the upheavals and the extraordinary resilience of life in the face of extremes. These cataclysms reveal the full complexity of the interactions between tectonics, the ocean, ice, and the Earth's crust. Simple geological adjustments can generate devastating mega-tsunamis over thousands of kilometers. Yet life has always adapted to these upheavals, colonizing the vacated environments. Some present-day species and landscapes, like the seabirds of the North Atlantic or the vast Eurasian steppes, are direct heirs of these deep reconfigurations of the planet. By exploring these 5 major events, we discover a Neogene vibrant with instability and rebirths. Yet, life has always risen, reorganized, adapted. The Neogene is thus not a mere transition between ancient faunas and emerging humans. It is a key stage where much of the geography and ecosystems we know today were shaped. Finally, a simple observation of the seabed reveals the scars of these upheavals: unstable margins, deep canyons, active faults, fragile ice caps. These structures tell the story of past tsunamis and massive slides. Sediment cores extracted from the seafloor preserve precious traces: broken microfossils, displaced pebbles, mixed layers of sand, clay, and organic matter. By analyzing them, researchers have gradually grasped the magnitude of the dynamics that have shaped our planet for millions of years. Beyond geology, these ancient narratives shed light on current risks. They show that tsunamis are not exclusive to the tropics. The North Atlantic, Antarctica, or certain enclosed seas have experienced them. The Messinian crisis reveals how vulnerable a basin can become once its hydrological balance is disrupted. The Storegga slide, in turn, reminds us that even tectonically calm areas can tip over due to a simple imbalance. In the era of climate change and rising oceans, these lessons from the past underline the urgency of incorporating geological history into coastal management. The Neogene offers a vast panorama of geological catastrophes where water and land continuously clash, shaping, destroying, and then recreating landscapes. These events are not only red in sedimentary strata, but have also reshaped the distribution of marine and terrestrial species by opening new habitats. Thus, after the sudden return of the Mediterranean Sea, mollusks from the Atlantic found a rich space to reconquer. Similarly, following major tsunamis, algae, seagrasses, and corals had to migrate to spared areas, leading to new dynamics of colonization. When we contemplate the current biodiversity, we understand that they are the direct heirs of these past geological dramas. The Neogene, with its tumultuous dynamics, illustrates the deep continuity between the history of rocks and that of living beings. These cycles, where land and sea embrace and then repel each other, have erased old boundaries, opened new passages, or destroyed others. On the scale of long times, they remind us how the face of the planet is in perpetual transformation. And with each upheaval, nature has been able to adapt, showing resilience that still resonates today in the face of contemporary environmental challenges. Thus ends our journey through the Neogene. Behind each submarine slide, each glacial subsidence, each dried or abruptly filled basin, lie colossal forces, capable of generating giant waves, impacting marine and terrestrial life, and reconfiguring landscapes. It is over hundreds or thousands of kilometers that the Earth's power is expressed, inviting us to both wonder and humility. The early Pleistocene era, spanning approximately 2.6 million to 300,000 years ago, is marked by profound climatic and geological upheavals. The Earth then experiences a succession of glacial ages in more temperate phases, dictated by orbital variations and the climate's internal dynamics. The ice sheets, vast expanses of ice covering the continents, shape landscapes and directly influence sea levels. The latter, regulated by the phenomenon of eustasy, falls when the ice expands, then rises during phases of melting. But beyond these variations, the early Pleistocene is also marked by the appearance of powerful tsunamis, caused by volcanic collapses, immense submarine landslides, or the sudden draining of glacial lakes. To understand the genesis of these tsunamis and their effects on ecosystems, some notions are imperative. A tsunami is a sea wave generated by a sudden displacement of water, most often caused by an underwater earthquake, a landslide, or the collapse of a volcano near or under the ocean. Unlike classic waves formed by the wind, a tsunami unleashes its power in the open sea, spreading at high speed over thousands of kilometers. When it reaches the coasts, it often begins with a sudden retreat of the sea, followed by a water wall that can reach several tens or even hundreds of meters in extreme cases. The impact on the coastline is devastating. Indeed, the flooding is accompanied by powerful return currents that can sweep away everything in their path, up to several kilometers inland. In the early Pleistocene, glaciers played a key role in tsunami formation. At the margins of the ice sheets, immense glacial lakes form, like Lake Agassiz in North America. When an ice or sediment dam gives way, billions of cubic meters of water suddenly pour out, creating a wave similar to a tsunami. Less spectacular than those caused by earthquakes or volcanoes, these flows can nonetheless submerge vast territories and reshape coastlines. Around 450,000 years ago, a section of the shield volcano on Fogo Island in Cape Verde collapsed into the ocean, causing a mega-tsunami. This type of volcano, with its gentle slopes and fluid lava, can collapse suddenly if its supports give way, sending tens of cubic kilometers of rock into the sea. The generated wave would have hit West Africa with extreme force. On certain shores, rocky blocks displaced to more than 770 meters above sea level bear witness to the power of this event. The consequences of these tsunamis go far beyond the immediate damage. As the water recedes, it leaves behind a profoundly altered coastal landscape. Specialized coastal plants, such as those in the intertidal zone, are destroyed or buried under saline sediments, rendering the soils sterile. Coastal forests lose many trees, either uprooted or suffocated. In the sea, shallow habitats, notably coral reefs, suffer from silting and abrupt changes in salinity or temperature. These disruptions are exacerbated by the heat released by the submerged volcanic rocks. In this context, marine organisms must flee or quickly adapt. On land, large mammals, in search of fresh water and fertile areas, are forced to migrate, thereby permanently altering the distribution of species in the region. Several 100,000 years ago, the Storegga slides off the coast of Norway caused powerful tsunamis. These events, occurring notably 800,000 and 500,000 years ago, were caused by the collapse of sediment masses accumulated on the continental margin, weakened by the pressures related to ice caps. When an entire section slides into the abyss, it displaces a huge amount of water, generating waves several tens of meters high. Marine deposits found far inland in Britain testify to the magnitude of these tsunamis, capable of redrawing the coastline. The coastal fauna, particularly large herbivores in search of pastures, suffered heavy losses during these sudden inundations. During the early Pleistocene, living species had to adapt to constantly evolving environments dictated by climatic cycles. The shifting zones of vegetation, steppe, tundra, and boreal forest forced the fauna to follow the resources. The recurrent tsunamis further complicated these adaptations by fragmenting habitats, disrupting migrations, and forcing certain species, like the woolly mammoth or the woolly rhinoceros, to alter their routes. In this unstable context, early hominids slowly began to extend their presence, especially in Africa and Eurasia. Aside from glacial and volcanic phenomena, tectonic movements of continental margins also played a role in generating tsunamis during the early Pleistocene. Around 350,000 years before our era, the Myanmar margin provides a striking example. There, the subduction of an oceanic plate beneath a continental plate caused major earthquakes. During one of these, the abrupt uplift of the seabed is believed to have triggered a large-scale tsunami. According to geological data, this wave would have swept over shores located several hundred kilometers away, disrupting ecosystems and reshaping littoral fauna. At that time, archaic hominins were already living in Asia, often near rivers or coastlines rich in resources. But these areas, conducive to subsistence, are also the most exposed to tsunamis. Although archaeological evidence is scarce, certain clues, displaced tools, or marine deposits covering sites suggest that these populations face these disasters head-on. A wave can obliterate an entire camp, taking away food, shelters, and human lives. Survivors often have no choice but to flee, temporarily abandoning these now hostile habitats. Tsunamis also transform coastal landscapes by depositing layers of sand and gravel that temporarily sterilize the soil. These devastated environments are first recolonized by pioneer plants adapted to poor soils. Gradually, organic matter accumulates, enriching the soil and attracting insects, small mammals, and eventually larger herbivores and their predators. Despite the initial violence, these areas eventually revert to dynamic ecosystems, proof of nature's resilience. In Southeast Asia, the coastlines, rich in biodiversity, notably host mangroves, essential ecosystems that shelter fish, crustaceans, birds, and reptiles. During the early Pleistocene, similar formations likely already existed. A tsunami can annihilate these amphibious forests, threatening endemic species. However, paleontological observations show that these environments regenerate over several centuries, thanks to sediment deposits that promote rapid recolonization and the emergence of new ecological niches. Beyond the immediate destruction, tsunamis can play a role in species dispersion. By carrying plant debris or tree trunks on which small animals like rodents or lizards take refuge, they create natural rafts capable of traversing long marine distances. While the majority of these animals perish at sea, some may reach distant shores where the absence of predators favors the establishment of new populations. This phenomenon, although rare, thus contributes to biogeographical diversification in the long term. The study of natural archives allows the reconstruction of traces left by these tsunamis in sediments. Sedimentologists and paleontologists search for layers with inclined laminations, pebbles deposited on fine structures, or unusual mixtures of organic matter and marine sand in terrestrial areas. These clues are distinguished from storm deposits by their greater power and transport capacity. Through radiometric dating or electronic spin resonance on quartz, researchers attribute these deposits to specific events: landslides, repeated Storegga slides, or major earthquakes along the Burmese margin. Over time, scientists have refined their models. They now simulate the propagation of tsunamis over thousands of kilometers, incorporating bathymetry, underwater topography, and the shape of the coasts. These simulations, compared with geological data, reveal the amplitude of past floods. On the Burmese margin or off Norway, future reactivations remain possible, with tectonics and sediment instability still active. These upheavals of the early Pleistocene show a dynamic Earth, where glaciers, volcanoes, and faults sculpted the landscape. After each tsunami, life reinvented itself, while hominins, in search of survival, adapted to the whims of a constantly moving and hopeful world.